Hello and welcome to our Wolfram Technology webinar, New in Wolfram Language version 14. My name is Thomas Pornweiser. I'm working at the Unisoftware Plus GmbH. We are a company based in Berg in Upper Austria, having around 50 employees from the backgrounds of theoretical physics, software engineering, and data science. We are a Wolfram Technology reselling partner, and our customers are Austrian universities, as well as the Fraunhofer Gesellschaft in Germany, and others, of course. We provide license and installation support from your order of Mathematica until it runs on your machine. And we also provide technical support when you are using Mathematica. Of course, we are not experts in every area, but we provide support as good as we can. And then, of course, we have also our experts from Wolfram in our background, which then in turn can help you. We have also other business areas in data science, industrial mathematics, with focus on simulation and modeling, as well as financial mathematics, where we have our Unrisk product line. And we provide consulting and project partnerships in data science projects, as well as in Wolfram technology related projects. If you want to contact us, please do so at our email address office@unisoftwareplus.com. Now to our main part of the presentation, the new features in Mathematica or Wolfram Language version 14. Wolfram Language version 14 was released in January this year. And as we can see from the graphics below, the number of built-in functions has been continuously increasing since the very first version of Mathematica, now approaching approximately 7,000 built-in functions. And with every upgrade of the Wolfram language, the number existing functions have been enhanced with respect to their scope of applicability, as well as with respect to performance, and there also were lots of bug fixes again. In our first part of the presentation, I want to present the integration of large language models in the Wolfram language and Mathematica. I think this is the most interesting part, maybe, because it's such a new and emerging technology. Mathematica provides seamless integration of large language models in the Mathematica frontend, which is known as chat-enabled notebooks. And of course, aside from chat-enabled notebooks, you also have the programmatic possibilities for interacting with large language models. Let's first have a short look at chat-enabled notebooks. They have been introduced in version 13.3. And if you can create a new chat-enabled notebook using the file menu, new, and chat-enabled notebook. Here in the chat-enabled notebook, you have available a new type of input cell, large language model prompt cell, which is providing different personas. The default persona is code assistant. This is a pre-trained model for which knows Mathematica syntax a bit better and probably can help you with more Mathematica related questions. But you can also have a plain chat with the original large language models. So if you want to use chat-enabled notebooks, you have first to set up your service connections, which you can do here in the edit command, edit preferences. And when the preferences dialog pops up, you can see here a new section, AI settings. If you switch to the services tab, you can see that I have configured OpenAI as default service and the GPT-4 model as default model. In order to get such a service connection, you simply here press the connect button and enter your API key from your OpenAI or Anthropic account. So it's worth mentioning that now in version 14, also Anthropic and Palm are supported as service providers. So the Mathematica language itself is more or less agnostic of the service provider and the concrete large language model you want to use, which is quite uh, a good design choice. So let's enter first demo prompt, and let's see what we will get as answer. Okay, as a second example, we can ask also more Wolfram-related question. If you want to have a new prompt input cell, you can use the period or single quote key. It will give you a new prompt input cell. And let's say we want to plot certain trigonometric functions. I want to plot basic trigonometric functions in the range from -pi to pi. And let's have a look what the large language model gives us back. So here from the output, we can see that the large language model indeed provides us a Mathematica command which achieves the goal I wanted to achieve. You can use those buttons here to paste it directly into your notebook. For example, if I press this button here, I get a new computation input cell containing the generated code. And we also see another interesting fact, namely that the large language model also has the possibility to use tools provided by Mathematica. So let's have what is a tool? You can configure tools here also in the preferences section in the AI settings when switching to the tools tab here. And you can see when I'm using the code assistant persona, I have enabled all those tools here. And for example, there is this Wolfram language evaluator tool. What does this do? So if you enter a prompt here, this prompt is sent to the large language model, and the large language model can then instruct the Mathematica frontend to use the Wolfram language evaluator tool. How is this done? If we pop up the large language evaluator cell here, we can see in the raw tab that the large language model gave back as answer a tool call instruction, which is interpreted by the Mathematica frontend. It generates here the plot, and then the result of the generated output is sent back again to the large language model, which can then further improve or continue with its answer. So it's a dialogue between the Mathematica frontend and the large language model for creating a good response which is presented to you. The last thing I want to show you here is that as you know from other chat interfaces, when you ask a question here, what is my name? All the information above the chat input cell is also provided to the large language model so that it can answer this question. Of course, it always depends also on the token size of the large language model, how much of the history can be transferred to the model. But in this case, the response is correct, as you can see. If you want to start a new chat with a new history, you can do so by creating here a new side chat. So if I'm creating a new side chat and ask the same question again, what is my name? You can see that the model then cannot answer the question because it has no information. Okay, let's return to our presentation. Coming to the programmatic interaction with Wolfram language and large language models. There is this new large language model configuration object which represents various parameters and promptings you can use for interacting with large language models. And the default configuration is visible in the $LLM evaluator system variable. So if we evaluate this here, you can see that the model and tool selection is both set to automatic. So it's basically what we configured in the preferences dialog. And then there is the LLM synthesize functions, which you can use for send prompts to the large language model. For example, who are you? We have seen this prompt before in the chat notebook. Or the more interesting example is, for example, here, give me a short poem about a fish with 4 lines. And then as an example for changing the large language model configuration, we can do so by creating here a new large language model configuration. It's using the default configuration and sets certain parameters to values you give. So if we want to use the GPT-4 model, for example, with a temperature of 0.5, and there is also the possibility to amend all of your prompts with certain instructions which are always given to the large language model. In this case, we instruct the large language model to always answer in German. And if we use the same prompt as before with the new GPT-4 German LLM configuration, we will get a German poem. The next thing which you can use is the LLM function, which is basically a template for prompts you can reuse. We can see here, for example, a template for creating a textual representation of share price statistics. So the placeholders here, 1, 2, and 3, are replaced by the parameters you give to the LLM function. We will see this in the example shortly. So let's first fetch some share data from, or stock data from Microsoft from yesterday. And if you use the finance story with the parameters exciting, Microsoft, and the data, it will then create an exciting summary of Microsoft's share price yesterday, giving all those facts here, all those share data. Okay, we can see here the output, an exciting story about all those facts. And the next thing is you can also use LLM prompt and LLM resource function. There are several useful prompts here also available at the so-called new Wolfram prompt repository. You can, for example, have adjusted the persona of your large language model, or you can use functions. For example, an interesting function here is, where was it? Was it modifiers, output formatting, I think. There is the numeric only, for example. It instructs the large language model to answer your question with a numeric, just a numeric answer. There are also functions for using a dataset representation. Dataset form here, I think it's called, right? And you can also here see all those examples on how to use those. Here as an example, I'm using the LLM prompt numeric only. It fetches the predefined prompt from the Wolfram prompt repository, and we can use it in an LLM function. So we have here a prompt template. If the first argument is bigger than the second, return 1, otherwise return -1, with the additional instruction that the output should only be a single number. And the textual response from the large language model, the digits are then converted to a Wolfram language integer. And I'm calling this function common sense size compare. And if we, for example, use the common sense size comparison of elephant and turtle, it responds with the integer 1. So the elephant is bigger than the turtle. At least this is what the large language model thinks, and I think which most of us will agree with. We can use then this function also in Wolfram language functions. For example, we can sort now a list of things by their size according to the large language model's perception of what things are bigger and smaller. As a final example, I have also here a clickbait title, resource function. So if I want to call my Wolfram language talk here a bit more clickbaity, I can do so. Another interesting thing is that you also can use examples, textual examples of what you have, input and output of what you want to achieve. And to provide this to the large language model, for example, if you provide here an input of a sentence, John is a 52-year-old male who is 6 feet tall, should result in a dataset, Mathematica dataset representation having all those facts with Mathematica constructs for representing the age and the height as Mathematica quantities. And you give here several examples. You do this and use this name, age, height extractor for the following text. You will get out really a dataset representation of all the things the large language model can infer and extract from this text. And one more thing, of course, is because we have here all those outputs in quantity representation, you can directly use also further Mathematica functions for unit conversion, etc. So you can really use this for further computation in the Wolfram language directly. Then as final thing, there is also the possibility of programmatic chat interaction. So basically the same thing we have seen in the chat-enabled notebook, you can also do programmatically. For creating an empty chat, you simply create a chat object, and then you can add prompts to the chat using the chat evaluate function. What is the tallest mountain? And let's give a different question here. On which continent is it located? So you can see here we have an in-place chat representation, and as Mathematica object you can inspect various properties. So we have here all those timestamps when the prompts were sent and when the responses were received, and various meta information on that. Now we come to part 2. What is new in the core language and with respect to mathematics? First of all, COMAP and COMAP apply have been added to the Mathematica language, which I personally find neat because they are natural counterparts to the map and apply functions which have been around in Mathematica for a long time. You have truncate sum for evaluating or working with infinite sums, and with solving equations with many roots have been improved. There are numeric vector and contour integrals, structured matrices and optimized algorithms, as well as computation in finite fields have been enhanced. So first, let's come to COMAP and COMAP apply. COMAP and COMAP apply are the counterparts to the map and map apply functions. So what does the map function? It applies a function f to each of a list of arguments here. So f of x, f of y, f of z is the output, quite naturally. And now the dual thing to do is to have a list of functions and to apply a single argument to all of those functions. You can do now this using COMAP. And in case when you have a function taking not one but several arguments, for mapping you used map apply, which applies a list of tuples to a given function. So again, this has been around a long time, and the counterpart is now having a single tuple, argument tuple, which needs to be applied to a list of functions. You can use COMAP apply, and you get this output. And as a final example, there is also an operator form for COMAP. So I'm defining here a function min, mean, max, which extracts from a given list its minimum element, its average, and maximum. Next, we come to truncate sum. Truncate sum makes it easy to work with inactive or unevaluated sums or infinite sums, which pop up quite frequently when you're working with DSolve or asymptotic or exact, etc. So as a first example, if we have here this generic infinite sum and we trunc it to the first 5 terms, we get really the first 5 terms of this infinite sum. And we can also apply it to, for example, the Taylor series of sine. Can have the first 8 terms for the Taylor series of the sine function, and we can also use it in, for example, plots for visualizing better and better Taylor approximations to the sine function. Numeric solve has been improved by using a new algorithm based on so-called monodromy. This now makes it possible to find systems with many roots, or for example, like this system here with a trillion roots, you get the roots quite fast, 5 of them, and you can also use it for special functions which could not be solved before. As an example, here we have this airy AI function in this equation, and if we are solving this, we get the roots as well, which has not been possible in earlier versions. Another improvement with respect to numeric computation is that there has been added numeric line integrate, numeric surface integrate, and numeric contour integrate. And as an example here, I have picked certain three-dimensional object, which looks like a squished donut or something. And if we use a vector field with divergence 1, like this here, we can use the numeric surface integrate for computing its volume. And those new numeric functions here can be useful alternatives to some symbolic computation. So getting quite quickly numeric results for complicated cases. Finally, there is also structured matrices which have been improved. There are symmetric matrix, Hermitian matrix, orthogonal matrix, and unitary matrix constructs now in Mathematica. Those are merely wrapper objects for or representations of matrices, which allow Mathematica to use more specific and more optimized algorithms for certain cases when you know the underlying structure of the matrix. For example, let's create a symmetric matrix from a lower diagonal table. So symmetric matrix is really an object here, and you can get the underlying raw matrix data using the normal function or the normal representation. And you can also query the algorithms for which are specialized for symmetric matrices now. As you can see, conjugation, conjugate transpose, pseudo-inverse, etc. All those algorithms are specialized for symmetric matrices are available. As an example here, let's create a symmetric random matrix of size 300, 300, and you can quite quickly compute its pseudo-inverse because Mathematica knows its internal structure. It will also return a symmetric matrix again. Okay, we will skip the rotation matrix example in order to go on with the next part. It is in finite field. Finite fields have been around in Mathematica for quite a while also now. It has been improved with respect to the operations which can be carried on, but let's first recapitulate what finite fields are about. So you can create here a finite field of size 7 to the power of 5. And all the elements in the finite field are indexed with numbers, and in order to retrieve the element with index 12,345, you can use this syntax, and you can calculate with those field elements. So if we inspect this field element A, we can see that it is a finite field element. Its type is, or head is, finite field element, and it is treated as an atom. So it is really for Mathematica just as good as an integer or something, which you can compute with. You have also the possibility to retrieve field elements not only by index, but also by defining or specifying the underlying polynomial coefficients of the element. And you can see that, for example, for the coefficients 1, 2, 3, 4, 5, you get back the element with index 13,539. You can retrieve information about the final fields and also about field elements. So we can see here the irreducible polynomial which is used, and we can see how many elements are in this field and its characteristic. And in case of the element A, we see its index, its polynomial coefficients, and to which field it belongs. All those is not new, but what is new is that the realm of computations has been improved. So for example, you can factor polynomials with finite field coefficients. And you also can compute with matrices having coefficients in finite fields like matrix powers or determinants, and of course also inverse. So that's the demonstration that it is indeed the inverse matrix. Okay, this is all I wanted to show you in the realm of mathematical and core language. And of course, there have been lots of further enhancements in the domains of image and audio and video manipulation, as well as the knowledge basis for chemistry and biological organisms has been extended significantly in version 14 now again. And we have improved visualization and graphics primitives. Also in the domain of astronomy, computation of solar eclipses has been further improved. And there have been lots of more updates and enhancements. For a complete list, you can look up the documentation or have a look at Stephen Wolfram's blog, where he announces the version 14 of the Wolfram language Mathematica, where he in detail walks through all of these new features. First thing is new primitives with respect to graphics and visualization. A so-called haloing graphics primitive has been added. Can be useful for in this example. You have a quite noisy graph and you want to highlight a certain curve within this graph. It can be a bit clearer if you additionally add some haloing, in this case a white haloing for this curve, so that it's a bit clearer now. And what's interesting or nice is that there has been added interactive highlighting. It's a new graphics option called plot highlighting. For example, here I'm using the plot highlighting with thickness 3 and red color, non-transparent color. So if I'm having this noisy data again and I'm hovering with the mouse above these graphics, the corresponding curve will be highlighted as I have specified above. And plot highlighting has also been added as default options for your normal plots. So for example, if you plot sine and cosine here and you hover above the curves, you will see the coordinates displayed according to your mouse position. There are several plot or highlighting styles available, which are listed here. And in case you need static highlighting, not based on the current mouse position, but at a given position, you can use the placed directive, which produces the plot highlighting at the given position 7. The next thing I want to show shortly is that texture mapping also has been improved. So there are certain ways of projecting your textures to the three-dimensional objects. And for example, here I'm using a cylindrical equidistant texture and a spherical texture mapping for producing a graphics of the Earth. But you can also place the camera inside such a sphere and use also a spherical projection to give the illusion of a background where you can place your three-dimensional objects in, just as an example. What's new in astronomy? The computation of solar eclipses has been rewritten, handling now more eclipses and with higher precision. For example, we can have a look at the solar eclipse map for the next solar eclipse. Note that the date is now outdated. It's now, at the time of recording, it's now after the 8th of April. So the next solar eclipse will be in the Pacific Ocean somewhere. And when will it be? It will be on the 2nd of October. And the maximum eclipse point in time is computable using this function here. And you can also retrieve the geoposition of this maximum solar eclipse point. This brings me to the end of the presentation. For further reading, just consult Stephen Wolfram's blog, where he is introducing Wolfram Language 14 and presenting all new features. And there is also a Wolfram U course, which you can walk through and where you can download various example notebooks. Also very, very good for getting an overview. If you want to know more about large language models and Wolfram Mathematica, my colleague Roman Wahl has a very good presentation on that, which you can have a look at here. And finally, as I said, all new features and enhancements are listed also in the Wolfram language documentation. I thank you everybody for your attention and wish you a nice day. Bye.